Hello, everybody, and thank you for attending my virtual talk entitled Quantifying Hydrologic Connectivity at the Continental Scale, Drivers and Implications. My name is Admin Husic, and I did this work in collaboration with my graduate student, Alexander Mikulek. I am an assistant professor of water resources engineering at the University of Kansas, where I lead the eco-hydraulics lab. On the bottom left there is me at the Rocky Mountain National Park, where I did some pondering on the topics of today's talk. And this is my dog, Darcy. She has no relevance to this talk, but I love her so much and wanted to include her. Okay, so let's go to the introduction. What is landscape connectivity? Well, connectivity is defined as a degree to which a system facilitates the transfer of water and matter, and it links terrestrial and aquatic ecosystems where it can provide fuel in the form of organic matter and inorganic nutrients from the uplands to in-stream ecosystems, such as what we've shown on the left here, where a particle traverses a path from A to B. What are the drivers of connectivity? Well, geology, climate, geomorphology, and human activity can provide bidirectional impacts on connectivity. There are two paradigms of connectivity that emerge: structural, which is defined as the physical template of the landscape, and functional connectivity, which describes the dynamic exchanges between the systems and the components. And the controls of both of these are recognized to vary across spatial scales. Today, we'll be focusing mostly on structural connectivity. So how do we quantify structural connectivity? Geospatial indices are really useful for this, as they use high-resolution topographic data to give an indication of connectivity. And on the left here, I've shown the index of connectivity, which is one such kind of tool, where you look at a reference element, this pink dot, you integrate the information upstream of it, and then also the path that it has to travel to arrive to a stream down gradient. And then you weigh these and you get a map of connectivity for the region, where you might have high connectivity in places that are near the channel or that have high gradients, and low connectivity in distal ridges with low gradients. And this is just a result of an index connectivity map on the left, and then also some field verification of high connectivity, that red area in the map identifying this gully, and then low connectivity, the green area identifying this depositional area. So what are some of the open questions in structural connectivity analysis? Well, one, how does structural connectivity of hill slope to stream pathways vary from basin to continental scales? How does the resolution of the data you use impact and incorporate a microtopography to inform connectivity? And is hill slope to stream structural connectivity modulated by tectonic or climatic drivers? So what we did was we loaded in the 18 HUC2 regions and the 332 HUC2 basins of the contiguous United States. We download a digital elevation model at 10, 30, and 90 meter resolution, which was an immense amount of data, about 25 terabytes in total. We generated stream targets, and then we mapped upslope, downslope components, and the index of connectivity for 80 billion cells in the continental United States. And these are the results we got. So on the top left, we see the map for CONUS of IC. And we see the structural connectivity is greatest in basins that drain the Rocky Mountains and the Appalachian Mountains and the Pacific Northwest, whereas the lowest values appear in basins adjacent to or near the Gulf of Mexico and the southern Atlantic coast, and also in areas in the upper Great Plains and west of the Great Lakes. But it's important to note that even within a watershed that may have overall low IC, there can be locations that have elevated IC, such as this basin in southern Kansas that has overall low IC, but then there are places within it that have elevated connectivity. These are four maps I wanted to show that describes four different kinds of watersheds along the connectivity spectrum. The Salmon River is the most highly structurally connected basin in CONUS by our analysis, whereas the Salton Sea is one of the lowest connected because it has incredibly flat areas, some man-made, some induced by climate and evaporation. And the Upper White River and Chesapeake Bay are other end members in this analysis. How does high resolution DEM data inform connectivity? Well, here we have this residential area and this cloverleaf interchange in a field. This is about 1 kilometer across. If we go to 90-meter resolution, we see the main river channel, but not much else. As we go to 30 meters, we start to pick out some of the tributaries off the main river as high connectivity. Then when we go to 10 meter, we can actually pick out that cloverleaf interchange a little better and more of the tributaries. And finally, at 1 meter data, we don't have this nationally, but we do in Kansas. We can even pick out roadway drainage ditches and other high conveyance features. So if we plot the kernel density functions, we see that the higher the resolution, we're identifying more and more of the highly connected structural features. So microtopography is really important. And these highly connected features typically make up 0 to 5% of a watershed's area. And across CONUS, they're about 2% would be classified as high connectivity. So what about the drivers? Well, we looked at 3 tectonic drivers: peak ground acceleration, the steepness index, and the concavity index. And we looked at an array of climatic drivers, but I'm only presenting 3 here: the precipitation, the potential evapotranspiration, and the wind speed. And one thing to note is there's a high degree of spatial variability across the CONUS landmass. So perhaps this spatial variability in these drivers could also influence spatial variability in structural connectivity across CONUS. And these correlation plots show that for tectonic drivers, the steepness of the main rivers and tributaries, it has the strongest control on hill slope connectivity. So the steeper the main river, the more well-connected the hill slopes are. River concavity and peak ground acceleration from earthquakes also has a strong positive relationship, but not quite so as the steepness of the main river. For the climatic drivers, we found the wind speed has a strong positive relationship with connectivity. So the greater the wind speed, the greater the index of connectivity, whereas the precipitation and potential evapotranspiration had relatively weak relationships. So what are the implications of these results? Well, I investigated some hydrologic extremes as well as the distribution of wetlands. And what I found that the higher the structural connectivity, the greater preponderance, or rather a greater propensity, I should say, for landslides. So the greater the structural connectivity of hill slopes, the more landslides occur within a basin. And that's what we see here in this strong relationship, both at the region and basin scale. However, lower structural connectivity didn't necessarily correlate with more floods occurring. Initially, I hypothesized that lower hillside connectivity might have led to ponding or slowing down of water transport, but that bears out a little bit at the region scale, but not much at the basin scale. But this could also be due to a limitation of the data set, where we only have about 420 extreme floods for CONUS, but we have about 3,500 landslides. So potentially with more data, we might see stronger relationships. And then lastly, what I see here is that as we get lower connectivity, index of connectivity, lower hill slope connectivity, we actually get a greater concentration of wetlands within a basin. So that's an interesting result there. But structural connectivity is just one component of the transfer of hydrologic information across boundaries. To fully understand the implications and how we should manage these connections, we need to develop functional connectivity models too. So if you're interested in collaborating in this kind of work, please reach out to me. Thank you all again, and I want to thank the data sources as well. So if you have any questions, please reach out to me via email. Thank you and have a great day.